Hi guys, welcome to Learning Electronics Repair. I have a box here, fairly plain brown box, okay, and this has something quite new in it. So this is from FNIRSI again, who are very happily sending me their new products now. So this is a 2-in-1 digital phosphor oscilloscope. It says 180 megahertz bandwidth, 5 millivolt division high sensitivity, high voltage, anti-burning protection, just underneath me there, 500 mega samples per second, okay, real-time sampling rate. And FNIRSI sent me this for free, but as ever they are not paying me to make this review, and I am free to give an honest opinion what I think of the oscilloscope. So let's take a look at their website to see what they say about this oscilloscope, and then let's have a look, make our own mind up. Well, here we have the oscilloscope on FNIRSI factory store. I've seen these on AliExpress at a variety of prices actually. They're saying it has a 20 megahertz signal generator, 180 megahertz minus 3 dB analog bandwidth. My understanding is that at minus 3 dB it shows half the amplitude it would at 0 dB. So I think they're saying it's 180 megahertz, the amplitude is about 50%. But if it's showing the waveform, and we will compare this again with my Rygar a little bit later, which is a 50 meg scope, but would actually display waveforms as high as my signal generator would go, which is 225 meg. So we will certainly be pushing this a little bit and having a look shortly. We have handheld dual channel oscilloscope then, the same specs we've just seen. It has XY mode, okay, FFT spectrum analyzer, okay, cursor mode, chopping wave output. Oh, this is something I was reading about before I received this. Okay, so apparently this can sample part of the waveform that it displays and then output that through the signal generator. I'm not quite sure what the limitations are, but it can do that. And it can also store a high number of waveforms, which might be useful if you're making comparisons between a known good device, especially if you repair a lot of the same thing, like a games console or something, for example, or a graphics card. It may be useful to have a backup gallery of known good readings. Okay, grayscale and color. Not quite sure what that actually means, but it's waveform refreshing rate. It looks like this is so effectively you can find glitches in the waveform maybe. 3 trigger modes, automatic, single and normal, rising and falling edge, fairly standard. Language adjustment. Trigger suppression. Okay. Large time-based scrolling mode. Zoom. Okay, 2 to 1,000 times magnification. Okay, might be useful. XY mode, something you don't normally see on digital scopes. Not quite sure how well it would work, but maybe we can try that. And it's saying that you can limit the bandwidth to 20 megahertz. Okay, I'm not totally sure why you would want to do that, but then I use scopes to fix stuff mainly, not for experimental or lab purposes. Okay, 20 meg function generator. And this, what we were discussing, cut a part or whole part of the various signals measured by the oscilloscope as the output signal of the signal generator and can store up to 500 customized signals. So this is what I would say, you can sample some incoming signal and then output that through the signal generator. Okay, 400 volt high voltage, quite nice. Fast charging lithium battery, so this is isolated. This should be okay to work on power supplies. Let's see how safe it is to do that with this on hot ground. It has the automatic adjustment thing, which we see on a lot of these scopes, but we can, I think, probably set it manually as well. Yeah. Cursor measurement between 2 points. Put your cursors, measure the voltage between them, and no doubt frequency, I'm guessing. Simple spectrum display. Okay. I'm not sure if I'll be able to test that facility. We can try, maybe. Screenshot saving, image export. So we have quite a lot of things to play with this. This digital phosphor relates to the display. Apparently this is like a analog scope display, phosphor, but it's a digital scope. I've not come across this before. Maybe something a bit new, but this says it has it. I'm just reading now. It sounds interesting what this does. The scope of it might be beyond this quick test video, but it does sound very interesting. Let's see if we notice anything when we're testing this. It says the spectrum display is not a spectrum analyzer. Okay, so I'm not sure exactly what it is. Function can qualitatively view the spectrum components of the current signal. Let's stick a square wave in and see what it does. That's a good idea. This is nice. It says the analog front end is all high voltage resistant design. So I think this is not a situation where we're going to blow up the oscilloscope if we put a 1x probe on and connect it to a high voltage. That I do like, if that's what it's saying. It looks like that's what it's saying. Okay, withstand a voltage of more than 400 volts in any gear. I think it means in any range without being burnt out. Okay, so we have lots of nice shiny pictures and information. Let's look at the scope ourselves and let's see what we make of it. Well, we have the usual oscilloscope probes I found with FNIRSI stuff. These seems to be quite nicely made scope probes, as good as any other ones I use. 200 megahertz bandwidth it says on them. They come with the little trimmer tool and the various little coloured rings and things. So there we go. Yep, fine. The instruction manual. This is probably like the other ones I've seen for their scopes. So quick description of the interface. Okay. XY mode it mentions. Signal generator. Okay. Clipping wave interface. Okay. I'll have a look at that. Quick description of the buttons. Explain what the buttons are and a quick operation guide. So this is fairly similar, and then it will probably give you some typical applications and how you would use it. Okay. Seems to be quite a lot to this. Yeah, common problems. Okay. So that's what we have in the way of instructions. It's always mentioned this about the signal over 5 megahertz being attenuated. This will tell you need to use a 10 times input. That seems to be common for all of these oscilloscopes, to be quite honest, due to input capacitance. Okay, so that is something we will just keep in mind. It's saying on the times 10 range, the bandwidth is 200 megahertz. Only when using the matching 200 megahertz probe. Okay. Here we have a charger, a charging cable, USB-C, of course, and the oscilloscope. First impressions then. It's quite chunky. The connectors for the meter probes are kind of hidden in there. That's quite good. Good for when you're working on high voltage stuff, that is for sure. Plasticky, flexible type sleeve, which, yeah, it looks like it does clip off if you need to change anything. I'm not sure whether the battery is interchangeable or not on here. Okay. One thing I have noticed is there seems to be like another plasticky cover on here. Okay. Yeah, almost like we can see some mark on it. No, that's a bit of hair, but now I have a thumbnail on there, of course. Okay. Yeah, can you see it's like got air bubbles in, as though there's like a plastic layer that should come off, but I'm not quite sure that it should. Can you see it there? I'm really not certain about that. I actually had a quick look at some other people looking at this, and I think one or two people elsewhere are not quite sure about that either. I will give this screen a quick wipe over with a cloth though. This is the sort of thing you use to wipe spectacles with, basically. Yeah, and you can see we get like a reflective thing there, like a surface. Let's go again. Yeah. So I'm not sure about that, to be honest. Let's try switching this on. Oh, that's bright. That is bright. Yeah, that is definitely bright. I mean, that is really bright. Those of you who remember those old scientific calculators in the 1970s, the Sinclair ones, that were like this kind of bluish cyan colour that light the room up in dark. Yeah. I had one. I used to get it out at night and just use it because it was so bright. I liked it to light the room up. Okay, so yeah, that display is really clear compared to other ones I've looked at. Very clear. This has a little stand on, so we can stand it up. Let's just zoom out a little bit. Yeah, so that's nicely angled on the desk. It's angled as a kind of, well, I can show you. There you can probably see how that is angled on the desk, maybe less than 45 degrees, 30 degrees or something, but it makes a very nice position to work with. Let's put some signal into this and let's have a play around. Yeah, let's see how intuitive this is to work with. And if that fails, let's get the instruction manual out. I've connected my signal generator. I've put a signal at 10 kilohertz, which is basically what it's displaying here. I've also had a quick look in the menu. So if we go into the menu here, we can switch on and off various options. I've switched on the cursor measurements option, and I've told it to show the frequency and the amplitude. There was plenty of other options in here we can play around with, but that's one I have set. So we can come back out of here on menu, and you can see we have a frequency display, also the time in microseconds, so kilohertz microseconds, the voltage 1 and voltage 2, and that refers to where these cursors are. So to move the actual cursors to where we want them on the screen, if we want to measure, for example, the time between 2 points or the voltage between 2 points, we go to menu, cursor measure, then we press modify OK. We can switch on or off. You can see the various options. Once we've done that, we press menu again and we're here, and now I believe we can move these cursors around. Yeah, so you can see I can move it to a certain point, for example the top of the waveform, the bottom of the waveform, and you can see the voltage peak to peak is basically what it's showing there between the 2 points. So I can actually set that where I want it to go. Okay, I can do the same with the horizontal cursor there, you can see, so I can actually move it to where I want it to go, and I can measure between 2 points. What I have noticed is there's like a minimum distance at which you can move it. You can't kind of like move it between those graduations. From what I can see, one quick press will do that, okay? Oh, that time I did get in between. So that is actually the cursor measurement, and this is now telling me the frequency between those 2 points, which is not the frequency of the waveform. You can see I'm not at the peak of the waveform on both of them. Okay, that basically is now at the peak, so 10.16. So yeah, that works reasonably well. What I think I will do with this oscilloscope, we can just have a quick look around some of the buttons if we just figure out the main settings for this. So we have channel 1 and channel 2. Yeah, again for channel 2 I can enable it or disable it. I've set it to 10 times probe. We have the coupling mode. We have FFT display. We can switch on or off. Press It again, it brings us back to here. Same for channel 1, as you can see. Okay. H plus and H minus, I think, is a horizontal time base. Yeah. Faster, slower. And this is this Fourier analysis thing that I switched on channel 1. I will confess I don't know enough about that really to know exactly what it is doing, but it's a feature I've not seen on a scope like this before. Comments below, guys. What's it useful for? Can I use it in my repair work? Okay. I'll switch the FFT display back off again then for the moment. Okay. That's back off again. Then I think menu comes out of there. This is probably gone now. Yeah. So that's how you switch it on and off. As I say, I'm not totally sure how I would use it, but who knows? We have the buttons H minus, H plus, V plus and minus, and T plus and minus. These I think are the trigger, the horizontal time base and the vertical amplitude. So if we go to H minus, yeah, that makes the waveform smaller, bigger. So this is effectively a lower frequency scan, a higher frequency scan. Okay. This will set the amplitude of the signal, yeah. And we can see at the top of the screen, it shows us the time base in microseconds, okay. Fast, he says, very fast actually, okay. We'll try a high frequency waveform on that a little bit later. Amplitude, okay, we can change that. So that seems fairly simple to use. This should be the trigger point. Yeah, I'm moving the green arrow. You see the side. Once I actually go outside of the waveform, I lose the trigger, of course. Okay, that's nice. Can move the waveform up and down, and you see that actually keeps the same trigger point as it should do, really. Okay, you're not moving the trigger point in the waveform when you're moving the waveform. That is nice. The blue tracer is just picking up background noise from whatever's being picked up on my bench. You can see that. For now, actually, I'll just switch channel 2 off. Okay, we just have a single channel at the moment. Okay. And that's the basic use of a scope, really. I mean, obviously, there are more things you can do with this. We have save P, yes, screenshot saving. Saving the waveform as it was describing we can do with this. Okay. What's move do? Slow movement. Oh, I see. This is how we can actually position the cursor better, I think. Okay. Fast movement. Yeah. Okay. Original. That I think goes back to the auto and puts the waveform back in the position when we started. Okay, so that's basic use of the oscilloscope. What I'm going to do with this is to test it in the same way I've tested all of the other ones I've looked at, which are some real life scenarios. We'll use the same ones we've always used, and let's see how this scope works in our repair work. If you've watched my other reviews of oscilloscopes, then you'll know the format I use. I'll do the same again because this is the best way to compare the performance between these tools. This is my little RF signal generator, so I normally like to see just how fast I can push these oscilloscopes. First of all, I have it set to 7.2 megahertz, and we'll just hit auto. And it should, yeah, there, and it gives us like a kind of a crinkly looking waveform. Now, this signal generator is not very good at generating sine waves at these frequencies. It's effectively a clock gen, really. It's not really what it was meant to do. But as we go up higher in frequency, we get what looks much more like a sine wave. So that really is the signal generator. It's not the scope, okay? Just move backwards and forwards. Let's see if we can just alter the adjustment. Yeah, we can alter this quite easily. Amplitude, time base, okay, trigger. Let's go up again to the next band. Okay, the amplitude has changed. You see it's still rather a crinkly looking sine wave. But also notice if I put my hand by this, it's actually going smoother. I mean, this thing is just on a PCB sitting on my desk also, which is probably not the best way to be running something like this. One day I will build this into a case. Okay. 14 megahertz. 15 megahertz. You'll see the trigger is near to the top of the waveform now. Let's just adjust it slightly. There we go. 17. 21. Now that's actually getting quite a bit smaller. And I'm going to compare this, I think, with my other scope just to see how it looks. But we'll just go up first between the various waveforms back to a proper one again. 28, 50 megahertz, 100 megahertz, 130, 144. Okay, let's turn it up more. We're into the megahertz scale now. Okay, going up. Hit the auto on this again. I think just set the time base, otherwise I can do it manually. Okay, we have a sine wave, and this is above its rated performance, so at 206 megahertz. Okay, now it's kind of like starting to lose it a bit just there, I think. But bear in mind I'm above the 180 claimed. We're actually on the fastest time base as well. So yeah, above about 210 megahertz it can't display the waveform anymore, but it is displaying the frequency. Almost. At about 218 it will display the frequency, okay. But we're getting like these artifacts and glitches in the waveform. But as I say guys, that is above the rated performance of this oscilloscope. What I would like to do is just compare it with my Rigol and have a look at some of these waveforms. So you see as the frequency is coming down, the amplitude is coming down a little bit. Okay. And then we get some rather strange waveforms. Okay, let's see what the Rigol does. Okay, so you can see both of these scopes on there, and as I was saying, this signal generator at lower frequencies does not particularly give a good sine wave. Okay. But you can see a difference definitely between the two displays. Okay. And what I do notice is the amplitude on this one is changing, but also the amplitude on the Rigol is changing as well. So there's not that much difference. You can see they both changed again, but we got like a different shape display, but neither really like a sine wave. Okay, we need to set the trigger point on this one. Okay, I'll just increase the amplitude as well. But it seems that the Rigol is displaying more of a sine wave than this one is, and keeping more of a constant amplitude as well. And I haven't particularly noticed this with the other FNIRSI oscilloscopes, to be quite honest. See some jitter in there. So it seems the Rigol is definitely giving a better display than this, especially at higher frequencies. I mean 27 megahertz now. You can see the two of them. Okay. The Rigol is getting smaller, this one's getting bigger, but now at this frequency we're at 50 megahertz. This actually seems to be doing a better job of it. Okay. But I think generally speaking the Rigol is working better. 100 megahertz. Well, my Rigol is actually set to be 50 megahertz. It's not modified in any way. It is a 50 megahertz scope. There you are, I can trigger it to just get in there, but it's got a bit of a jitter now. That's the 100 megahertz, that's beyond the capability of the Rigol really, but it is still displaying a waveform, as is the FNIRSI, but that's within its rating, 130. And you can see it changes again, so both of these scopes, if you like, are acting in different ways. Okay, let's go up again if we can, or we have to go manually, 144. Yeah. Again. 220. Okay. And now this one is struggling the more. The Rigol actually is managing to display that reasonably well for a 50 megahertz scope, I will say. But at this frequency, they both have some jitter. It's what you'd expect, I guess. This is now struggling to give us a waveform as well. So, yeah, 216 compared with 220. So much above 180, and it won't really give a particularly accurate display. It will show us a waveform there. Sometimes for repair work, that's all we need to know. Okay. Let's now try the other tests I normally do. So we'll look at an audio signal. We'll look at a motherboard, we'll look at the real-time clock, at the 25 megahertz clock, at the VRMs, we'll look at the BIOS to watch it being accessed, and then we'll do some tests on a switch mode power supply looking at the drive to the transformer. So audio waveform, really any oscilloscope should be perfectly capable of doing this. We'll just check, just click ground on, it's the phono plug. This is coming from my speaker. I'll increase the vertical gain a little bit. Yep, there we go. I'll decrease the time base a little bit. Okay. There we have what's starting to look like an audio waveform. Let's press auto and see what that does. Okay, yeah, it's put it in there in the middle. It'll be interesting to see what that Fourier analysis thing does now with this. Let's have a look. So we can go to, I believe it was on menu. No, it was down here, FFT display. Let's see what this does. Okay, menu. Yeah, we have like another display on there, which I believe is giving you something like the range of the amplitude at different frequencies. That's just a sideways movement. We can increase the time base somewhat. Okay. I'm not totally sure if that is actually useful or a gimmick. It's something that we have. Okay. So audio waveform, absolutely fine, but you'd expect that. Let's get a motherboard and start checking some clock frequencies and similar. One of the things we may be most interested in looking at is the VRM on a motherboard. So I'm now connecting to the MOSFET with the scope probe, you can see there, and I'm going to just hit auto and see if we can see the waveform. And we can see the waveform there quite clearly. So this is running at 293 kilohertz. You can see the pulses there each time the MOSFET switches on and off, and I think we can also see effectively the ringing effect. Yeah, so you can see it rises, rings, drops and rings. So this is the coil ringing at each end of the switching pulse. Okay, that's actually quite nice. I quite like that. Yeah, you see that quite clearly. Okay, so that is a VRM running and it looks good. Let's look at the crystals. We'll go to the real-time clock, which is here. This will be quite a small waveform. Let's see if we can see it. Again, I will hit auto. Let's have a look. And yes, we have it there. So 32 kilohertz, 33 kilohertz. This is a very small waveform. I'll just try to change the trigger point slightly. Okay. I will say it's not giving me exactly a stable frequency read. I hope that's in focus for you guys. Try there. Okay, well, we can see that it is running. Yeah, we can see it is running. Let's look at the 25 megahertz crystal. So that's over here. I can just find it. Well, we can see something, but I'm not sure that is it. I may be in the wrong spot. Let me just try again. Yeah, there it is. So 25 megahertz very clearly. Okay, that is the 25 megahertz clock on the motherboard. And the last thing we might be interested in maybe is to see if the BIOS is being accessed. Let's have a look at that. So normally the BIOS is only accessed when the board boots up. And the easiest way to test is to go on the chip select pin on the BIOS chip. You can see here main BIOS and backup BIOS. Let's try and zoom down a little bit. Okay, the chip select is on pin 1, which is here. And I'd expect normally there wouldn't be any activity on there. We'd only get something when we actually switch the motherboard on. So I've switched it off, I'm going to switch on, and what I expect to see is a sequence of pulses here. Yep, there you see it's accessing the BIOS many times, and then the board boots. Okay, we can just decrease the time base a little bit and we'll have another look at that. Okay, so we'll switch it off, switch it back on again. There, you see it. I'm not sure what auto will make of that because it only happens when we first boot up. Off again. Go again. Yeah, and now you can see it. Okay, you can see definitely it is accessing the BIOS. Okay, so that test is also passed, but again, you would expect any oscilloscope to be able to do this really. The oscilloscope then did the basic checks on the motherboard. The VRM we could see quite nicely with the ringing as the MOSFET was switching off and on again. The real-time clock we could see. The 25 megahertz clock we could see. So let's now try this on our switch mode power supply and see how well it will allow us to see the drive waveform. Here is my test switch mode power supply. I normally use this when I'm working with oscilloscopes to see how well they work. This has a single output voltage. At the moment there's nothing attached to it here, you can see. So this will be running effectively not in standby but in low power mode, so it's not driving any load. The inductor we can see here, this bead, this is actually connected to the MOSFET in here, so directly to the coil. So if I clip my oscilloscope probe on here, then we can actually see the drive coming from this chip. Now, the thing with oscilloscopes and devices like this is we have to clip the ground somewhere. So we're going to put the ground onto the hot ground here. Well, this isn't isolated. This point here effectively, in fact actually, connects to the mains directly through this bridge rectifier. So on one half cycle, this pin is connected to the neutral, and on the other half cycle, it is connected to the live via this bridge rectifier. If we connect something here that's grounded, we're just going to short out the mains to ground, okay? That means I can't use my Rigol oscilloscope, the bench oscilloscope, but I can use this one. So to do so, I'm going to clip my ground lead onto here. This is hot ground, okay? I've actually connected the ground lead from one scope, and I'm actually going to use the other one to probe without the ground lead attached. Now, this is relatively safe, but I have to say relatively, because this point here is actually connected to hot ground. So the ground on this scope probe is the same as on the other one. And if we measure from here, hot ground, to here, you'll see we have continuity. So this part of the scope probe will be floating at this half mains voltage. Half the time it's live, half the time it's neutral. And the same applies to that part in there as well. Just get onto it. So the safest way to do this is either A, to keep your fingers away from that, or B, to put the clip back on. So I'm going to put the clip on. and I'm going to clip this onto the output from the IC here. I do suggest when you're working on stuff like this, you do it this way. Don't just probe around with the scope. If you slip, you short something out, first of all, you'll probably damage or destroy the device you're trying to repair anyway, or to test. And B, it's just not very nice to do that. Yeah, flash and the bang, nobody really likes it. Well, maybe the bang. But there we go. That's beside the point, yeah. The other thing is that the shielded part of the BNC connector here is also connected now to hot ground. Put my meter back in again. If I go onto here, you'll see it's connecting to hot ground, and both of these are connecting to each other. So we now have effectively mains voltage on here as well. This is why I said this is quite a nice design, because you've made it relatively difficult to stick your fingers down there. Yeah, if you want to be stupid you can, but you're not likely to do it accidentally. That's the point. Yeah. The other thing when you're doing this, don't connect the USB to something, especially something that's grounded like a PC. Otherwise you will know very rapidly when you switch on that you've made that mistake. Okay, so we're ready to go. I could have just used one probe. This is the way I commonly work. I use one probe as my ground point and the other one as my scope probe. It's just the way I've worked really for a long time, because this little lead is quite short. So if you do it this way, you can put this wherever you like. You haven't got to think, oh, the lead isn't long enough to ground. Okay, now we'll plug the power in then. This is not switched on at the moment, by the way, but I'm going to switch it on now, and let's see what we find on our oscilloscope. Well, you can see we have a voltage. Well, I've spotted the error of my ways, or rather the error of my scope probe position, because that's the wrong place. So we'll actually clip it onto here. This is switched off at the moment. Okay, put the scope back on. Then let's try again. Okay, I'm expecting this yellow trace to go up off the screen somewhere because of the high voltage. So I'll bring it down towards the bottom actually. Let's see what it does. Well, it's up there at the top. And let's see if we press the auto button. I think you saw the pulses already there, yeah? Just watch. I'll get rid of the blue trace because we're not connecting it to anything. So that one we can just switch this to off. Okay, menu. And if we watch, we should see some pulses on here. Can you see it every now and then? There. There. So that's the power supply effectively just pulsing. I'll see if I can manually position this a little bit better. That's actually at the bottom of the adjustment. Auto. There we go. And now you can see it. So auto's done it quite nicely. And you can see that the power supply just continually sends, if you like, a pulse. That's because there's no load on the power supply. There's nothing to discharge the output voltage, so it's kind of like in low power mode at the moment. Let's switch it off and let's attach a load. You'll notice actually now the voltage is coming down. It's still running, by the way, the power's off. Okay, little burst of drive. So gradually it's discharging the large capacitor. Okay. Till eventually it reaches a low enough voltage where it stops. You can see with no load on it takes some time. Okay, now I think it's stopped. I'll put a load on. Okay, this is a 20 ohm resistor. I have two of them here. I'm just going to use one of them. So this is a 12 volt supply. So a 24 ohm would give half an amp. A 20 ohm is a bit more than half an amp, maybe 600 milliamps. That's fine for this power supply. I actually have this wired up so I can connect the resistors in parallel, giving myself a 10 ohm load, or I can put them in series to have a 40 ohm load. It's quite a handy little thing just to keep in the workbench, really, this one. So we'll connect this to the output. I'll connect to the other end of the resistor to the ground of the output. Okay. And now let's switch our power supply back on again. And now we should see it continuously driving. There you go. Can you see it? Yeah. Just go to auto, automatic adjustment. Oh, and now you can really see it. So you can see that the MOSFET switches off, switches on, pulls power through the coil, and then switches off again. And we get this ding, 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 this ringing effect before the next time it switches on. This jitter is not the oscilloscope jittering, this is the power supply jittering, if you like, to maintain the output voltage. Okay? You see it very clearly there, very nice. So we can easily use this on high voltage circuits because of the anti-burn thing. We don't have to worry about putting the probe in one times and damaging it. It will take 400 volts at least anyway. So I do like that. So to sum up then with the oscilloscope, the things I particularly like with this is, one, the very bright display. That is extremely bright. Yeah, it's a really nice display. It's a dual trace oscilloscope, but you'll notice I haven't really used that in this review. That's because in repair work, very rarely do I need to use the dual trace, maybe occasionally, but I can't think of any time in the last 4 years, to be quite honest, I've needed to do that. But obviously it is a dual trace oscilloscope. We know it can display the sine wave at 180 megahertz, in fact up to about 210, and measure the frequency. Whether you want to call that a true sine wave is up to you, but generally speaking with repair work, I think what you really want to know is whether an oscillator is oscillating, or whatever the signal, is it there or is it not there? That's usually what you want to know. With the high voltage testing, I've had 1 or 2 of these handheld scopes now. After this, I think this is probably the best one I've seen so far, in as much as the way they mount the probe. So unless you do something really stupid, you're not going to present your finger with a high voltage. And if you are stupid enough, well, it's not your fault, you know, not the device. I've been running this for quite some time, doing this review and just generally messing around with it, and the battery is down to about 2/3 now. It seems to have a very good battery life, so that I also like. I haven't gone into all the ins and outs of the specifications and features this has, because others will be doing that. I look at an oscilloscope as a tool. Will it do the job I want it to do? Okay, and if it will do the job I want it to do in these very scenarios, that for me is fine. That's what I want an oscilloscope for. You may wonder why I switched this off, by the way. The resistor is getting quite warm now, the load. That's actually why I switched that off. Nothing to do with the scope, okay? To sum up then, like many of the things I look at, it suits a certain task or a certain job. If you're doing repair, it's great from what I can see. There may be types of repair that this is not so suited for, but for what I do, it's perfectly fine. But I can say that really from pretty much all of the oscilloscopes I've looked at. So it comes down to, what features do you want? How much do you want to pay? This one I think is as nice as any of the other ones I've tried. So I will leave it up to you to decide whether it suits you or not. I think for the price, it's fine. Obviously, you guys, when it comes to test equipment, always have lots to say in the comments below. And that's great, you know, I mean, we've all got our own opinions of it. If I decided to buy one of these, as I was buying a handheld oscilloscope, I would be quite happy with what I've got here, because I know it's going to do what I want it to do. And really, that's as much as we can ask. Hope you enjoyed that, and I look forward to seeing you soon on another Word Electronics Repair video. Ciao for now, guys.